Hi, my name is Mark Krasinovich. I'm Chief Technology Officer of Microsoft Azure. Welcome to the Microsoft Developer Virtual Conference, and welcome to my keynote, Microsoft Azure, the World's Computer. Now, to describe Microsoft Azure, I'm going to focus first in this keynote on 4 areas of differentiation. They include productivity, trust, hybrid support, and intelligence. Then I'm going to spend some time talking about the core services of Azure, from compute to network to storage. In each of those, I'll talk a little bit about some of the innovations we have in those areas to show you that Azure is a platform that's constantly evolving and constantly improving, and we're leading with world-class innovation. But first, why do we call it the world's computer? Well, you got to turn to Satya Nadella's worldview for Microsoft, which is building a platform for intelligent cloud, intelligent edge. And not surprisingly, Azure is the foundation for the intelligent cloud. What you might not realize is that Azure is also the foundation for the intelligent edge aspect of that worldview. What that means is that Azure is delivering services and features and capabilities that allow you as a developer to write applications that span all the way from the public cloud down to the tiny edge and everything in between. And for enterprises to be able to manage resources, whether they're in the public cloud or out on the edge or in hybrid environments. This is all part of the Azure fabric. And the reason why we've chosen to make Azure focus on not just public cloud hyperscale infrastructure is that the world is becoming infused with intelligence. It's everywhere. It's ambient. It's around us. The 20+ billion devices that are out there, with billions more showing up every year, that are connected, that are managed, and that allow us to interact and manage the environments around us. But let's turn to those 4 areas of differentiation, and I'll start with productivity because that is the most important from the perspective of a developer, where you want to get your job done. You want to develop applications with the tools you want, and you want to do it quickly and focus on your business value rather than on infrastructure and mechanics. One of the first priorities for Azure is meeting you where you're at. Many of you are using open source technologies. Many enterprises are building their futures on top of open source technologies. And so for many years, Azure and Microsoft have focused on embracing open source ecosystems and participating deeply within them, really living up to the philosophies of open source and the collaboration that goes with it. That's reflected in a variety of different ways. One of them is the deep partnerships we have with open source companies, the companies that are behind technologies like Linux, including Red Hat, SUSE, Canonical, as well as the companies that are behind the most popular frameworks, whether it's Confluent for Kafka or whether it's Databricks for Spark. We support offerings for many of these companies as first-class citizens on the platform, and in many cases we partner deeply with them to make those offerings available. In some cases, like with Red Hat and Databricks, we launch services jointly with them that are branded as Microsoft Azure services. Those include Microsoft Azure Red Hat OpenShift and Microsoft Azure Databricks, with Red Hat and Databricks respectively. That means you're going to get the best experience in the public cloud for those offerings on top of Azure. But Microsoft and Azure's full buy-in to the open source philosophy extends not just to supporting open source technologies on our platform, but we actually build much of Azure on top of open source technologies. We also contribute Microsoft and Azure technologies to open source, whether it's Visual Studio Code, the #1 IDE on the planet, the #1 most active project on GitHub, or whether it's .NET Core, or whether it's PowerShell. Those technologies we develop, we use, and we contribute to the open source community. And if you take a look, that is really part of this overall umbrella of Azure being a great place to be productive, because it leverages all of these strengths of Microsoft as a company that's been focused on developers. Those include, like I mentioned, Visual Studio Code, Visual Studio itself, Azure DevOps, and Azure DevOps Pipeline for CI/CD workflows in the cloud. Azure DevOps is actually the #1 SaaS IDE, or CI/CD platform on the planet. And then, of course, you might have heard that we bought a company called GitHub a few years ago. GitHub is the place where open source collaborates. It's got more than 50 million active developers on it. It's got more than 45 million open source projects on it. And Microsoft is basically doing all of its development. for our public SDKs, for the frameworks that we make available, for those technologies I mentioned, on GitHub with the community. Now let's talk about trust. And Microsoft runs on trust. We know that we have to earn the trust of our customers for them to be willing to put their workloads and their data in our public cloud. One of the ways that we represent trust, and also one of the ways that reflects the way that we understand enterprise requirements for public cloud, is in the many certifications we have. We've got more certifications than any other public cloud, and not just that, we've got the deepest level of certifications. You can see from this slide, which shows a sampling of some of the certifications, they extend from international standards to regional standards to industry verticals, and there are many certifications we've achieved through the US government. But it's not just understanding enterprise security requirements and having those attested to with these certifications, it's also us building security deeply into the platform, and also honoring a principle that we've had from the start, which is first party equals third party, meaning if we need a technology to be able to operate securely, as an example, we want to make those same technologies available to our customers so they can also operate securely like we do. No better example of that than Azure Security Center. We use Azure Security Center to ensure that our services are meeting our own compliance, meaning that they do not have ports open to the internet, that they're have the appropriate version of the security pack installed. And Azure Security Center is built into the platform and made available to customers. One of the very unique and novel aspects of Security Center is that it comes with something called a secure score that you can see here in this picture. The secure score allows you as a developer, or you as somebody managing security on behalf of your organization, to understand the security posture of your Azure resources. And not only that, but then to drill into the score and understand where those gaps that contribute to that score are, that don't mean that it's not as high as it could be, and also to prioritize based off of the value of applying a mitigation. For example, if you're missing a web application firewall in front of an internet-facing port, you'll get told that by putting one in front, you'll raise your security score by a certain number of points. Not only that, but Azure Security Center will take you right into our marketplace where you can select from a variety of Microsoft's own and third-party WAFs which one you want applied to that port and have it mitigated immediately. Not only that, but Azure Security Center also demonstrates our hybrid focus, which I'll talk about next, which means that Azure Security Center can be used not just to manage the security of your Azure resources, but your resources outside of Azure, in your own data centers and on other public clouds. Speaking of hybrid solutions, Azure has been focused on hybrid from the very start as well, because we understand that enterprises are going to be in a hybrid posture. Those enterprises that are moving the fastest to the public cloud still take years to move. And many enterprises take 5, 7, plan out even longer journeys to the cloud. We want to support all of them with a consistent experience from their on-premises resources to the cloud across that journey. So that includes offering capabilities like the ability to back up SQL Server to the public cloud, or extend their on-premises identities up into the public cloud using Azure Active Directory and its single sign-on capabilities where you can use that on-prem identity to sign on to cloud resources. But it also includes services that allow you to take Azure out to the edge, whether that edge is in your own data center or out on an edge as part of an IoT solution. One category of offerings we've got is called Azure Stack, with offerings like Azure Stack Hub that let you take essentially a consistent version of Azure out to your own data center with as little as 4 hyper-converged servers, where that includes infrastructure services, some platform services, Azure's control plane and key management, as well as Azure's portal. And that means that you can take an application that you've deployed to public Azure, and if you want it to be consistent, also have it target Azure Stack in your own data center. That portfolio of devices continues to grow and includes things like Azure Stack Edge, which is the storage appliance that comes with compute, where you can do machine learning out on the edge in your own environment on top of Azure container managed instances or virtual machines. It also more recently now includes Azure Arc, which lets you take Azure's management plane out to your own data centers. We launched Azure Arc back in November with the announcement of 3 initial capabilities, one of them being servers and virtual machines, another one being Kubernetes clusters, and another one being Azure Data Services, where there's Postgres or SQL analytics clusters that run on Kubernetes outside of Azure's data center. With all 3 of these and Arc enablement, now you can manage those with Azure Resource Manager's control plane, which gives you consistent monitoring, consistent identity, and consistent governance, as well as APIs to manage those services out on the edge and outside of Azure's infrastructure. And you're going to see more and more integrations with ability to manage resources outside of Azure through Azure's control plane. And then finally, Azure IoT. Azure IoT lets you take those devices that are out on the edge and manage them from public Azure, meaning deploy compute to them, get telemetry off them, manage their identity and security. Those include Azure IoT Edge Runtime, Azure's SDK, and there's many companies in India that are taking heavy advantage of Azure IoT, including L&T Construction, one of the top 5 contractors in the world. If you went to the airport, or you're going to go sometime soon hopefully, that infrastructure is almost certainly built by L&T Construction. As well as Piramal Glass, which is building intelligent factories that are connected through Azure IoT so that they can manage the health and get analytics off the factory floor and optimize those processes. The final area of differentiation I'll focus on is in the area of intelligence, which includes artificial intelligence and machine learning, and is heart of our intelligent cloud, intelligent edge aspiration. AI is going to infuse everything we do, from whether it's ordering something online, interacting with our customers, even AI Ops, which helps us run our applications better. But Microsoft's got a very unique asset in this area, and that is Microsoft Research. We've got labs all around the world, and many of those labs are focused on machine learning research, which they've been doing for decades now. You can see some of the many breakthroughs that they've made just in the last few years, whether it's getting a human parity on the ResNet vision test for object detection, or machine translation human parity on Chinese to English or Chinese to text, or machine parity of humans on understanding spoken conversations. Those research breakthroughs don't just sit as academic results. They actually make their way into Azure. They do so in a way that's very easy for you to consume as a developer through our cognitive APIs. Those APIs span 6 different categories, from vision all the way to knowledge. And those APIs are simple REST endpoints that you can call with a query and get back an answer, leveraging those best-in-class machine learning models underneath. Not only that, but we're making it possible for you to customize many of those. So the object detection API, the one that achieved ResNet parity, might not recognize the objects in your environment that are unique to your factory floor, or unique to the space that you're dealing with, or the products that you sell, or the particular scenario that you'd like to detect. But with our custom vision version of that object detection API, with as little as 20 images, you can train a custom version and deploy a custom endpoint that your application can call to recognize those objects. Not only that, in the spirit of our focus on hybrid, we're making it possible for more and more of these APIs to be deployed into your environment, in your own enterprise data center or out on the edge, as Docker containers. So now you can take the API with you and have the data stay local to your environment because you want to save on bandwidth, or you've got security or privacy concerns on making that data available up in the public cloud. Now let's start our tour of the infrastructure of Azure, starting with the data centers themselves. Azure's got 61 regions around the world, which is more than any other public cloud provider. Just a month and a half ago, that was 58 regions. We continue to put regions in more and more countries because our customers require that data centers be close to them and close to their customers, and the data be stored within their sovereign boundaries. So we've designed an architecture where we've got geographies, which more and more are countries, like India, where we'll go in with at least 2 regions. The regions are going to be far enough apart that they can support independence with large-scale disasters. So in different electrical grids, different tectonic plates, and that allows customers to fail over from one region to the other in the case of a large-scale problem. Within regions, we are building high availability architectures with our data centers called availability zones. A region with availability zones will have at least 3 zones, where each zone consists of at least one physical data center that is isolated from the data centers in the other zones, meaning that they can tolerate a local flood, or a fire, or a power loss, and not affect those other data centers. That allows customers to build a synchronously replicating high availability solution across those different zones because they're close enough to support synchronous data replication. The combination of these two mean that you have high availability and disaster recovery. One of my favorite things to do is to show people behind the scenes of our data centers, our regions. Our Dublin region, which is our North Europe region, is one of the oldest in Azure. It launched originally with Azure. And here you can see DB3, which was launched in 2010, the same year as Azure, and DB4, which launched in 2013. You can see DB5 here, compared to those which launched in 2014. You can see the evolving evolution of our data center designs, where each one is becoming more and more efficient. And here you can see the continued build out over time, where we launched DB6 in 2015, DB7 in 2017, and DB8 in 2018. And then you can see the land that we've cleared for additional data centers as we continue to build out the Dublin region. You might be thinking, wow, that's a lot of power that you're consuming. What's the impact on the environment? And this is something that's top of mind for Azure and for Microsoft. Whether it means that we build the world-class, most efficient data centers, which are 93% more efficient than a traditional enterprise data centers with a PUE of just 1.189 aggregate across our entire fleet, where PUE of 1.0 means perfect energy in equals energy out. Or the fact that we have the largest green energy deals with 315 megawatts of purchased solar power as an example in Virginia, or 180 megawatts of wind power that we purchased in the Netherlands. But our commitment goes further than that. In fact, we've been carbon neutral for a while. We want to get to net carbon zero. Net carbon zero through the use of 100% renewable energy, which we committed to by 2025. But net carbon zero from Microsoft all up, and Microsoft all up going back to the very founding of Microsoft back in 1975. This is a commitment that you can see Satya, Brad Smith, and Amy Hood, our CFO, made a few months ago publicly with these commitments. Net carbon zero for Microsoft all up back to 1975 means we're going to pull out of the environment as much carbon as Microsoft has put in from its very start. That carbon that Microsoft emits through its campuses, through the shuttles that we drive around our campuses, through the air travel that employees make, through our supply chain, the creation of the servers that we put in our data centers by our suppliers, to the Surface Books that we sell to consumers, we're going to be offsetting all of the carbon that was generated in the production of those items as well. And then with our Microsoft Research asset, we've been focused on how we make our data centers even more efficient, including kind of out of the box or under the water thinking with Project Natick. Project Natick V1, Microsoft Research started with us 4 or 5 years ago, where they put a rack of servers in a sealed container on the 25 feet underwater. Now the idea behind Project Natick that they had was, hey, if we put servers in cylinders at the ocean floor, we'll run them with lights out operation, which means humans won't be messing with them, which means the servers might last longer. Further, if we suck the air and water vapor out of the environment that those servers are in, they might be subject to less corrosion, which will also make them last longer. Further, they'll operate at constant temperature. In fact, we can leverage the cool water of the ocean floor so that we don't have to heat them. And there won't be heating and cooling periods like you might have with a land-based data center as the air gets hotter and colder, just day to night and summer to winter. The initial project was successful. They powered on the servers. They ran for 30 days. So they started on Project Natick V2 with us a couple of years ago, which was to take servers from an Azure data center that was used for internal operation, deploy them on the ocean floor, and then have servers from the same batch operated in control experiments on land. The project demonstrated just one of the benefits here of having this cylinder-based deployment. In just 30 days from the time that cylinder was created in France, we were able to power on the servers and start serving internal Azure load on those servers 1 kilometer off the coast of Scotland in about 100 meters of water. Now it's been about a year and a half when we already have the preliminary results of this experiment, testing what this lights out operation in this cool environment. And the fact is, these servers have just 12.5% of the failures as their control versions on land. So already huge improvements in reliability for these servers, meaning lower costs for the servers, and those cost savings we can pass on to our customers to be more efficient. Now let's take a look at the servers inside those data centers. And to do that, I'm going to take you on a tour down memory lane for Azure. Starting back in 2010, just to show you how far Azure has come when it comes to the size of our servers and the capabilities of our servers. Back in 2010, we launched with servers that had 12 cores and 32 gigabytes of RAM. These were considered decent server class machines at the time with 1 gigabit NICs. And the fact is, they were great for those scale-out cloud-native workloads. But we had customers starting to come to the cloud with their enterprise scale-up workloads, in-memory databases, like SAP workloads, that wanted more memory. So we deployed what was at the time the largest server hosting virtual machines in the public cloud, what we called the Godzilla server, our G series of VMs. These had 512 gigabytes of RAM and 32 cores on them. And these were capable of running those workloads. But those workloads got even bigger. Enterprises were moving more and more SAP workloads up into Azure. And so we had to create even larger servers. With our Beast server here, they can see we launched just a couple years later with 72 cores and 4 terabytes of RAM on top of it. Now compare that to the servers we've been deploying just in the last couple of years. They're not as big as our Beast, but you can see with 512 gigabytes of RAM in the AMD Gen 6 high memory versions, they've got as much RAM as the Godzilla servers had just a few years ago, the ones that we considered real monsters. But these servers, these scale-up servers, even including the Beast, still not big enough. And so we had to create even bigger servers. And you can see the Beast V2 that we announced a while ago has 12 terabytes of RAM and 224 cores in it, for a total of 448 virtual CPUs. Again, the largest virtual machines in the public cloud. And then Azure goes to the other end spectrum as well in support of IoT. I mentioned these MCU, these microcontrollers that Azure IoT supports with our Sphere OS, which is highly secure on them. You can see that these are extremely small, have just 64 kilobytes of RAM and 2 M4 ARM processors on them. I have to use a magnifying glass just to see how they compare to our Beast V2s. But we continue to push the envelope when it comes to servers as well. One of the areas that we're looking at is in response to some of the trends that we see of energy consumption of servers and server parts in the data center. You can see that the CPU power profile has continued to grow. You can see that with GPUs that we've got for high performance computing and for machine learning, that the NVIDIA DGX2 machines consume a total of 10 kilowatts of power. By comparison, a rack provision power in a data center today is about 14 kilowatts. So that means we can put about one of these in the space of a rack in a data center, which isn't a very great efficient use of space. So we've been exploring air cooling technologies. The traditional servers we've got are air-cooled. And we contribute these air-cooled designs to Project Olympus, so anybody can take advantage of them. But we're also investing in liquid cooling. You can see different types of liquid cooling we're looking at. Microchannel cold plates, which is the kind, if you've got a liquid-cooled machine at home, you're probably using this, where water's flowing over plates attached to the GPUs and CPUs to cool them off. We're also looking at immersion technologies, like one-phase immersion, where we sit the motherboard or main board inside of a liquid to cool it off. And then two-phase immersion, where we dunk the whole server inside of a liquid with a very low boiling temperature, which has a great diffusion characteristics to really keep those servers cool, even at operating at very high power. We've taken those designs for liquid cooling and also recently contributed them to the Open Compute project. And then we're also working with partners on pushing the state-of-the-art on server parts. I mentioned how we bring the latest and greatest NVIDIA GPUs in, but we've got unique partnerships like one with Micron, where their 3D Crosspoint based technologies are being customized for Azure. These 3D Crosspoint parts have a kind of unique characteristic, because 3D Crosspoint is a memory technology, but it acts like an SSD. So it's got extremely low latency, but it's also durable, which makes them the best-in-class kind of SSD type technologies. Now, to demonstrate that in action, I'm going to show you a side-by-side comparison of Scudi in action. Here you can see two servers, one that's a traditional enterprise class SSD that we run in our data centers, and the other one which is a Scudi based virtual machine. I've got a tool on them called Iometer, which runs a benchmark that stresses them just by sending a bunch of IOs at them. And you can see that the NVMe device is to be able to sustain about 2 gigabytes of throughput per second. But you can see that the Scudi device is able to achieve more than 9 gigabytes per second. That's the kind of performance difference you can see. And with AMD, we've made it so that you can carve up these SSDs or these Scudi devices into multiple pieces and give different pieces to different virtual machines, making it a great cloud storage solution. Now let's take a look inside of Azure Networking. Now, Azure Networking consists all the way from our physical infrastructure, our WAN, the fiber connect to our data centers, up into software-defined networking offerings like load balancers, virtual networks, DDoS protection, VPN services, firewalls, to our edge connectivity solutions, which include ExpressRoute Direct, as well peering with ISPs, as well as our site-to-site and point-to-site VPN technologies. Speaking of our WAN, it's one of the largest WANs in the world. You can see that it's got over 150,000 miles of cable connecting our regions together. When one region interacts with another region, it does so over our dark fiber. We've got over 160 edge sites. We've got over 1 million miles of fiber just within a data center. And this WAN is continuously expanding. If you take a look, just as everybody started to shift to work from home, learn from home, play from home, we saw 40x peak traffic growth across our WAN. And you can see that those traffic spikes corresponded to the lockdowns around the world. Where China locked down, you can see the growth of 150% in the WAN usage there. Italy with up to 400% spikes. In the United States with close to 60% spikes. We had to expand our WAN rapidly, and this really highlights what the cloud was designed for. With all our processes, tools, technologies, supply chain that we've got in place, you can see that just in a few months, we added 12 new edge sites to support this expanded WAN demand. We added 25% increase in peering capacity, and in total added 110 terabits of capacity to our WAN through that time. And we continue to expand it. This would just be unheard of for an enterprise to expand their physical network in this way. In fact, we had to leverage our global supply chain in innovative ways to support the demand growth. You can see here our subsea cables, AEC and Maria being a couple of those subsea cables. Maria being one that supports 200 terabits of connectivity, the largest subsea cable on the planet. But you can see when Europe locked down, we started to see utilization on that cable grow. We needed to expand capacity on the AEC cable. However, AEC at the time was not an open cable, meaning we couldn't expand fiber capacity or bandwidth capacity on that cable. We needed to install DWDM equipment, dense wave digital multiplexing DWDM equipment, on either side of that cable to open it up. Purchasing new sets of those devices would take months. In less than 6 weeks, we were able to take DWDM equipment that we were provisioning in another part of the world that hadn't come online yet, borrow it, ship it to the US and Ireland, install it on both ends of that cable, open it up, and then you can see after we were able to open it up, the Maria utilization went down as we were able to better load balance traffic. But our innovations expand not just beyond expanding our physical network, but also expanding the capabilities of our software-defined networking. We believe in a cloud-native future, one that's built on top of containerization. Now, up to this point, containers have been second-class citizens in public clouds. To network them together, you need to apply what are called overlay networks, where those networks are invisible to the underlying cloud infrastructure. You use different tools to manage ACLs on them and routing on them and load balancing on them, instead of the native capabilities of the platform. We want to make containers first-class citizens on the Azure network. And so to do that, we've got a project called Swift, which is container underlay support. It works by giving a container orchestrator like Kubernetes or our own service fabric the ability to tell the underlying SDN network where a container happens to live and which virtual machine. By knowing which virtual machine it's on and which IP addresses it should be mapped to, it can integrate with software-defined virtual networks, which means all of Azure's policies, routing rules, network firewall rules, all apply now to containers as first-class citizens. Now let's take a look at Azure's Compute and Applications platform. The heart of it is Azure Resource Manager. I mentioned it before. It is the universal control plane for Azure. Everything plugs in to ARM on its control plane. So every single service, whether it's Azure Kubernetes service, or Key Vault, or Functions, or Event Grid, all plug in using what's called a resource provider. When they're plugged into the Azure Resource Manager control plane, that all traffic aimed at them goes through the Azure Resource Manager front door, where we can apply consistent logging through Azure Monitor and operational logs. We can apply RBAC rules. We can apply ARM configuration. You can deploy templates that span multiple resources. You can apply governance and policy across those resources in a consistent way. I talked about Azure Arc a little bit earlier, which is taking our control plane and plugging in resource providers from that represent on-premises resources. So ARM is ever more getting capable in managing resources. But compute is more than just the control plane, it's also the data plane. I talked about containers when I talked about networking and making containers first-class citizens. And we're doing that with hosting as well, hosting those containers. We believe in a future of cloud native and serverless, where you as a developer don't have to worry about the infrastructure. And we want to have the world-class platform for running containers. So we built something called Atlas, which is a secure multi-tenant container platform built on top of our own service fabric infrastructure that supports a variety of different APIs on top, including ACI for Azure Container Instances, which are serverless containers, to Azure Functions, where when you deploy Azure Functions for Linux, you're deploying them onto the Azure Atlas infrastructure. We'll have future multi-tenant services as well. The idea here is that those containers integrated with Swift and being serverless, now you have a world where containers don't have to worry about the infrastructure underneath them. You can focus just on the code running inside those containers. And we're also working on innovative ways to make containers more efficient. So if you're familiar with containers, you know that they consist of multiple image layers. Those image layers represent dependencies. At the bottom, you might have a flavor of Linux. On top of that, you'll have, for example, a Java runtime. On top of that, you might have a web framework. Those different images, when your application launches, have to be pulled down onto the server. And that can take a while. You can see here across different size of images or containers, the aggregate image sizes from 2 kilobytes going all the way to 5 gigabytes. If you've got a dedicated virtual machine and you're doing a Docker pull of those images for a 2 kilobyte container, that'll just take 1.8 seconds. But for a 5 gigabyte container, that takes a whopping 412 seconds. And that's just a matter of the network download plus the storage bandwidth to write those images to disk. And you can't launch the container until all of that download is completed. We've been working on something called Project Teleport. The idea with Project Teleport is instead of downloading the container images to the server, we simply map them as file shares. Each image is its own file share. We've done this in Azure Container Registry for Azure Container Registry tasks. When you have a container that runs as a task, it's leveraging Project Teleport to map those images in through Azure files. And what that means is that a mapping operation is very quick. And once the image is mapped, you can simply start the container on top of it. If the data is not locally present, it's going to be read in, effectively faulted in from the backing container registry. And you can see the just dramatic difference in performance that we get when we launch containers using Project Teleport. For that same 5 GB image, it takes just 7.6 seconds to mount and launch the container on top of it. So huge benefits, and the innovations are starting in Azure Container Registry. They're going to spread to usage of Azure Container resources everywhere across Azure. But we took a look at compute. It's not just about the containers and the infrastructure for containers. It's also about the application and programming models on top of those containers. And this is an area where we're also innovating. When we take a look at the demands on enterprise developers, they continue to grow. And at this point, customer expectations are when you write and deploy an application, it needs to scale out, it needs to be resilient, and you need to deliver these cloud-native capabilities. Now, you as a developer are focused on your business problem. You also have certain languages and frameworks that you want to use to build your applications. And when we take a look at the state of the world now, from the requirements that you've got to what's available for you, well, things like functions. Azure Functions are FAS, Functions as a Service, serverless infrastructure. You don't have to worry about the underlying infrastructure. You simply write the piece of code and deploy it, and it scales out automatically. That's great, but it's only supports as first-class citizen in a few languages. If you're a .NET developer or a Java developer, it's got a great experience. But if you're developing in something else, your experience is maybe not so good. And not only that, but when it comes to those functions interacting with other parts of your application, now you've got to bring in other services like a pub subsystem in between. Not only that, but once you've bound yourself to these specific versions of a pub sub service like Azure Event Hub, for example, you've lost a little bit of the portability you might need if you're developing a multi-cloud solution, or you're developing a solution that you'd rather use Kafka when you're running on premises. So we've been working on something called Dapr, a distributed application runtime, which basically implements a bunch of building blocks that you can take advantage of as a developer to make your life easier. The key fundamental idea behind Dapr is that it's implemented as a sidecar architecture. What that means is that you don't actually have to integrate into your code any Dapr code to use its facilities. You interact with it using a local HTTP or gRPC endpoint. And that means you can leverage building blocks from whatever language and framework you want to, whether it's Java, .NET, Python, Rust, Ruby, Go, name your favorite language, and you can use Dapr's capabilities. And those building blocks are there to offload a lot of the work that you might have to do. Like if you want to save state from your application, instead of importing an SDK for Cosmos DB, having to learn that SDK and then save state for your application, simply use the Dapr state building block. And that once you use this Dapr state building block, you've abstracted the underlying store. What that means is that you can plug in a Cosmos DB component when you're running in public cloud, a Redis component when you're running on-prem, and your application is completely portable. Now, these ideas might sound a little abstract, so why don't we make them concrete? And I'm going to do that with a demo here. With this demo, this is one of my favorite demos because the programming challenge I'm going to pose to you as a thought experiment, as you look at what I'm doing here, is you've been tasked to write a distributed calculator. A distributed calculator that's going to run on a Kubernetes cluster, where each button in the calculator is represented with a different microservice. Not only that, but you're going to write each one using a different language. You're going to run one in Python, one in C#, and so on. And we want you to deploy this and make it portable across different clouds. Meaning use native services if you're on Azure for storing the state of the calculator and for communicating between the microservices. And if you're on AWS or another cloud, use the services for that cloud. That seems like a monumental task. You imagine the thousands and thousands of lines of code, the SDKs you're going to have to learn. Well, let's just go look and see what that would entail if you leverage Dapr's building blocks and sidecar pattern. So here I've got the server, which is the front end of the calculator, which is a React application built on top of Express. You can see here it's got two Dapr URLs, a state URL and the Dapr URL for invoking other microservices. That state URL is the state store. That's where we're going to store the state of the calculator. So when you add 1 plus 1, it's going to store 2 there, so that if the calculator fails and you relaunch it, it's going to remember that the current state was 2. Now you can see that when we press a button in the user interface, that we're going to invoke different Dapr routes on that local endpoint. So you can see for when you press add, we're going to invoke the add method. You can see that these URLs are Dapr relative URLs. And what that means is you don't have to worry about name resolution, looking up the other microservices. Dapr worries about routing those messages. And so you simply do HTTP post to them, and they get routed to the correct microservice in the correct Kubernetes pod on the correct server. Let's take a look at those microservices now, starting with the adder. And you can see the adder here is written in Go. Here's the Go HTTP handler for the add route, and you can see that the adder simply takes the 2 parameters that were passed in as JSON and returns the output parameter. The subtractor is written in C#. Same idea. Parse the input parameters, return the output. The multiplier is written in Python. You can see it's using a Flask web server. And the multiply route there just multiplies and returns. The divider, written in JavaScript. You're getting the idea. And then finally, because we wanted to really show that Dapr supports literally any language, the modular operator is written in Fortran 90. So, any code, no SDKs. In fact, you're looking at the entire project, every line of source code. Now let's go ahead and launch that distributed calculator, and you can see when I look at the pods in my Kubernetes cluster, there's the adder, there's the front end, there's the modulo operator pod. They're all deployed and ready to go. Let's get the endpoint for my front end, which is a Kubernetes service. Here it is. Let's go launch it. And I'm going to have the developer view open in the browser, and you can see now as I type in numbers and operators, you can see the calculator calling persist, and that is the state store Dapr API. You can see it calling into the other microservices, subtract, add, so on. And you can see when I do a refresh here that because I've persisted the state and the current state is 1, when I do a refresh you can see the front end querying the state store to get the fact that it was a 1, and now I've got it back as a 1, so I didn't lose any state. Not only that, but Dapr works with anything that uses the OpenTelemetry API, and that includes application insights with Azure Monitor. So we can go into the application map view and see, without having to add any instrumentation to our application, exactly how these microservices talk to each other and relate, including the latencies between the executions between them, that show us that which one had the longest latency, which I'll let you figure out yourself, of which language had the slowest performance. But then, because this is in Azure Monitor, I can see a full list of all the API calls and the details of them that were logged by Dapr. Again, what I was able to do was build a distributed microservice-based application in multiple languages with no SDKs for any cloud or data storage service, and deploy it and run it and get insights into it. And because I can plug in the state store, I was using Cosmos DB here in Azure. I could use DynamoDB on AWS. I could plug in Redis on premises. The application is portable across those environments. So I recommend you check out Dapr, which is 100% open source technology. I even have contributed a component to Dapr. So our final look at Azure infrastructure will focus on Azure Storage. Azure Storage consists of a growing number of diverse interfaces as well as tiers of storage. And I think this is one of the trends that you're going to see in the public cloud, is because of all the different storage technologies we've got at all different price and performance points, we want to make that available to you so that if your data is hot, you can leverage SSDs and in-memory caches all the way down to cool tiers, which include archival storage, like tape that we've got in Azure. Further, because we have this amazing infrastructure that supports geo-distributed storage, plus low latency, plus efficient storage through ECC erasure codes, we want to make those available to you through multiple APIs. And on top of this Azure Storage Substrate, you have object interfaces, you've got disk interfaces, and you've got file interfaces. Object interfaces that include Azure Data Lake Storage Gen 2, that include Azure Blob Storage, disk interfaces with our premium and ultra SSD disks, and files, which include NFS and SMB. But we're constantly looking at ways of pushing the envelope. And again, Microsoft Research is just a unique asset we partner deeply with in Azure across all areas of our infrastructure. In the case of Azure Storage, we've been working with Azure, with Microsoft Research in Cambridge in the UK for many years now on looking at alternate technologies for storing data for archival purposes. One of the challenges with tape is that you've got to periodically reread it, meaning the tape degrades, and so you need to reread the data and then rewrite it back out. If we could leverage technology like glass, we wouldn't have to go reread, because glass literally lasts for thousands of years. And this was the premise of Project Silica, a research project that joined between Microsoft Azure and Microsoft Research. With Project Silica, the idea is that you write data into the glass three-dimensionally with something called a voxel, where with a high-performance pulse of energy at femtosecond, and how short's a femtosecond? It's a 1/4,000,000th of a second pulse, the same frequency of laser used in eye surgery. Short enough that we can write the data, but not disturb and deform the glass around where the data is etched. With a certain retardance and polarization angle, we can encode multiple bits. And you can see here 3-bit voxel being etched in the glass. I mentioned it's three-dimensional, so we'll store data in up to 150 layers of glass, and also with very short distances between those voxels. And that means the data can be stored at very high density. Not just that, but you can read the data out very quickly and efficiently, because to read the data, you simply flash light at the voxels and then read out the retardance and polarization. And that means that you don't need any special equipment other than light and cameras to read the data. So multiple benefits over a technology like tape or anything else literally that's been created for a long-term archival storage. And you might be saying, well, glass, that seems pretty fragile. Well, let's just see how fragile it is. Here's a home video put together by one of the researchers working on the project to see just how durable silica is. So we've taken a piece of silica with some data on it. We boil it. We degauss it. Don't do this with your disks. We scrub it with steel wool. And remember, it's okay to scrub the surface because the voxels are in the glass, not on the surface like a Blu-ray. We microwave it, we bake it. And the data is read out successfully. Very durable. And we announced a short while ago a partnership with Warner Brothers. It's going to transform the media industry, because today, media industry, their IP, they have to protect at all costs. And so what they'll do is take film, even if it's digitally produced, separate it into different colors, store it back onto real physical film, into different canistores, put it in a vault or a salt mine, and then periodically have to read it and write it out again, because film degrades over time even in those environments. Now we've reached a breakthrough with Warner Brothers where we stored and read back successfully the entire Superman movie from the 1970s. And when they store this, they'll never have to read or rewrite it, And it's also now resilient to all those kinds of things that we just subjected the glass to that would have destroyed a film. So also at a fraction of the cost, because glass based off silicon is one of the most ubiquitous materials on the planet, and so can be created with very low cost. So just one of the examples of Azure and Microsoft Research and Microsoft pushing innovation forward for the cloud. So with that, I want to thank you very much. I hope you have a great event. It's awesome to see you. I wish I could have been there in person. I hope to visit India in the very near future as soon as we're able to move around again and we're through these unprecedented times that have been challenging everybody. But at this point in time, the world needs developers more than any other time. So thank you very much.
Hi, I'm Brendan Burns, and I'm going to be talking about the past, present, and future of Kubernetes. I wanted to start with a warning that this talk has a bunch of opinions in it. This is my thoughts and feelings about both where we came from as a community and where we're headed as a Kubernetes environment and as Kubernetes matures from being a tool for operators to being a tool for developers. As with all opinions, I could easily be wrong, and the only way we're going to find out is the journey that we take together. So please take everything you see here with a grain of salt, and I hope you find it entertaining and inspiring for both where we came from and where we're headed in the future. So where are we with Kubernetes right now? Well, Kubernetes is present in every single public cloud at this point. There's over 90,000 commits in the GitHub repo. 2,500 people have contributed, and that's just to Kubernetes itself. It doesn't count any number of the ecosystem products that exist around the Kubernetes ecosystem. There's over 1,000 meetups, people getting together around the world to discuss Kubernetes. And I think more interestingly, and perhaps more importantly, Kubernetes has become the basis for next generation platforms. It's become a foundational layer that everything from platform as a service to functions as a service to machine learning programs have come to depend on and expect to be available that they can then build on top of. So it's been a really incredible journey. Truly, it has been quite a ride, corkscrewing our way through both the development of the project, the development of the open source community, the development of the ecosystem, of managed services like the Azure Kubernetes service, and many, many more. It's been an amazing ride to be on. I've felt grateful every single day that I've had a chance to participate in this community, to help lead this community, but also that people from all different places, all different countries, all different job descriptions have come together to produce this amazing ecosystem, this amazing community, this amazing product. So if you're one of those people, thank you so much. If you're thinking about becoming a part of our community, welcome. I want to talk a little bit about how we got to this place. How did we get to the present of Kubernetes, where it's in all of these public clouds, where all of these people have taken deep dependencies on it? Well, I want you to cast your mind back. I want you to cast your mind back to 2012. And I want you to be thinking about some of the themes that people were starting to think about in cloud in that time. In particular, things like dynamic API-driven infrastructure was just beginning to be an idea, right? Cloud had come along and provided APIs for creating machines, had come along and said, hey, look, you don't have to fill out an order form. You can just make an API call and a machine pops up. And in that world, ideas like immutable architecture, cloud deployment patterns like blue-green, and this idea of continuous software delivery, all of these ideas were beginning to take hold. They were nascent. Not very many people were necessarily using them, but these were the ideas sort of at the frontier of development. In general, the world of cloud in 2012 was actually not exactly that. A lot of people were SSHing into machines. A lot of people were running bash configuration scripts to deploy their software onto those machines or to reconfigure those machines. If they were getting a little bit advanced, maybe they were using an automation tool like Puppet or Chef. They were distributing their software as tarballs or zips. And the net effect of all of this is that they were creating snowflakes everywhere. They were creating these perfect, beautiful servers, but if that server ever had a meltdown, it was gone forever and it could never be recreated. It's a very problematic place to be if the expectation is that you're continually shipping software or that your application needs to scale in response to new users. And in general, it was a pretty scary world as a result. Very, very hard for people to believe and trust that they could roll out their software, hard for them to believe that they could respond to an event like the COVID-19 crisis that we've just been through, where demand to these services spiked to levels previously unseen. In general, people were a lot more afraid of their systems than probably they ought to be. Leading the way into sort of the new world, at least from my perspective, a lot of the time was Netflix. And they were talking a lot about their architecture, open sourcing a lot of tools having to do with the way that they were delivering software. And they really advanced this idea of immutable infrastructure. This idea that you shouldn't SSH into a machine, you shouldn't make imperative changes to machines by running apt-get install or by running some other script, by downloading things from the internet, but instead you should create immutable artifacts. In their case, it was VM images. You should create immutable VM images. Every week the build process builds not just a piece of software, but actually all the way through to a VM image. And then that VM image is deployed out to the cloud service. If you need to make a change, you go back to the very beginning, you run through the build process, you develop a new VM image, and you roll that VM image out. It really means that it's much harder for you to make mistakes. It's much harder for you to end up with those snowflake servers. But the downside of it is that VM images are actually quite challenging as a developer to deal with. You've got a very heavy, very sort of tightly monolithically connected thing that contains the whole operating system, the kernel, and everything else, and that's the thing you're trying to run on your machine. And frankly, even in modern times, more than a few virtual machines on any developer's desktop, and the whole system kind of bogs down. So it was a very, very heavy developer tool that the trade-off for that heaviness was that they were getting a lot of value in their operations and their deployment reliability. So into that world, Docker stepped, and Docker said, hey, actually, we can give you all of those benefits of immutable infrastructure, of immutable images, but with a more developer-focused look, with a more developer-centric view about how you could put an image together, how light it could be, how fast it could be to start. And so take all of the value of immutable infrastructure, but make it a lot more developer-friendly. And I think that is the key insight around why that hockey stick took off. Because for all of those reasons we talked about before, these ideas were moving forward, but it really wasn't until Docker containers came around that it was palatable for people. Now, what was it that the Docker container really brought? Well, the first thing that it really brought was this idea of an image package. Right? It used to be that you developed a bunch of stuff on your computer, you have a bunch of artifacts, you need to ship it to the cloud, and you figured something out. It was an exercise left to the reader to determine, how do I take all these distinct pieces, be it configuration files, be it images, be it the program itself, combine them together and get them to something that can run on the cloud. And even when you did it, oftentimes when you deployed it to the cloud, it looked a little different than it did on your laptop, and it didn't run correctly. So we had all sorts of problems with people saying, it's not running in production, and the developer saying, but it worked on my laptop. That class of problems is one of the first problems that Docker containers came along and solved. Because with that container image, the configuration of that package on your development machine is identical to the configuration of that package when it runs in the cloud. So you have that consistency of experience that means that the idea of it running on your laptop and not running in the cloud is no longer a problem that people go through. But of course, that's not the only problem that people have. People also need to distribute these images around the world. If I'm creating a service that has a worldwide scope that is replicated into data centers in Europe, in the United States, in Asia, I need to be able to push that image that I've created all the way around the world. And again, prior to the container image, this was largely an exercise left to the reader. Maybe you uploaded it to a storage bucket somewhere. Maybe you put it up, you use something like rsync to copy it around to all of the different machines. It was something that you had to think about, and something that therefore you might mess up. Docker came along and said, hey, we're going to give you a protocol for a registry. We're going to give you an image pull protocol that will enable you to easily distribute all those images around the world without thinking about it too much. And just like it running on your computer but not in production, distributing an image around the world suddenly became a problem that nobody had to think about anymore. It was a problem that everybody had, but nobody really wanted to care about. And the container came along, solved that problem too. And then finally, and most interesting to me, was this idea that the container was a unit of execution. A container was a thingy that I could sort of treat as an abstraction, but I knew it had a press play button. And given a program expressed as this container abstraction, I could think about building orchestration on top. And that's sort of the genesis of the Kubernetes project, was a bunch of us coming together and saying, hey, if everybody in the world starts packaging their applications in these container images, then that's a necessary precondition for us to build an orchestrator that can take those container images and deploy them out across a fleet of machines and provide a whole bunch of tools that enable them to put their applications together in an easier to manage and easier to use way. So really, that's the whole purpose behind an orchestrator. It's to take that image and to distribute it into this sea of compute, so that you're no longer thinking about individual machines. You're no longer giving servers names. You're no longer thinking about them as anything more than contributing a certain number of cores and a certain amount of memory and a certain amount of disk and maybe some GPUs or other kinds of hardware resources into this sea of compute, this aggregate sea of compute. But in order to take advantage of that aggregate sea of compute, you need an API. You need an API that can direct a container image and present an interface to you that allows you to think of that sea of compute literally as just a sea and ignore the fact that the machines are there. And that's really what the Kubernetes API was designed to do. It's designed to create this separation between the physical resources that provide capabilities and a container-oriented, logical infrastructure-oriented API that enables you to just deploy containers and for them to find their home on whatever piece of hardware happens to be the right place for them to run at that time. So with the Kubernetes API, as a developer, I can simply say, hey, I want 3 replicas of my web server running. And just like when I double-click on a program in my laptop, the operating system doesn't prompt up a dialog and say, hey, you know, what processor do you want me to run that on? Kubernetes says, you want 3 replicas of that running? I'll go and find 3 places for that application to run, and I'll place them there. And if one of those machines happens to fail, well, you know what? I'll actually move your application to keep it healthy. So that's an amazing capability that, again, means it's one less thing for me to think about. And if there's any theme that I want to really highlight in the development of containers in Kubernetes, it's that reduction in things that I have to learn about. It's making someone's life easier by limiting the set of things they need to worry about to the things that are focused on exactly what's necessary to make their application go, not the details of the infrastructure underneath. So what does an orchestrator do beyond sort of providing that API layer that focuses on abstracting compute away from you? Well, there's some really basic capabilities of the orchestrator. For example, service discovery. It wasn't just enough to say, hey, look, I can run 3 replicas of something. I want to also define a logical service and say, you know what, there is a service that's associated with these replicas of the container, and if I want to consume that service, I don't actually bother, again, not learning as much as I have to, I don't want to bother knowing how many replicas there are of that particular container. I don't want to know what their names are. I don't want to know what their IP addresses are. I just want to connect logically to my back end. And so again, this is another theme for Kubernetes, which is taking literals, taking physical infrastructure or replicas in a service, and turning them into logical constructs, turning them from, you know, backend number 4 to the idea of the backend service. This kind of decoupling makes it much easier for you to design and deploy your systems in an agile way because your teams are no longer having to tightly coordinate between their services. So at that point, we've built our orchestrator, we've gotten to the present, and so we're done, right? Kubernetes is available to you everywhere. The system takes away all of these pain points that people had way back in 2012 when we started thinking about these ideas. Mission accomplished. We can all run off to vacation land. Well, it turns out that it's not that simple. And in fact, I think as we look forward, when we think about cloud native development, though Kubernetes has done a lot to make it easier to deploy and to manage your applications, it's done very little actually to make it easy for you to build those applications. And so as we go forward and as we think about the future of Kubernetes and the future of services running on top of Kubernetes, these are really the themes that I want people to be thinking about. These are the areas that I think we need to do a lot more effort in. We need to build a lot more tools around. We need to, I mentioned about enabling people to learn less. We need to do more of that, right? We need to do more that enables people to just do the right thing without having to learn how to do the right thing, right? I shouldn't have to learn about how to monitor my software in order to deploy it. It should just be monitored. Likewise, I need to be able to take advantage of the best practices and the patterns that are available to people. I need to share in implementations of things so that I don't have to rebuild the wheel every time. Even if I'm really, really talented at building the wheel, rebuilding a wheel every time is a waste of my time, right? And the truth is that many people out there, actually need standard implementations. It's a challenging thing for them to develop a really great implementation of some distributed systems pattern or to figure out how best to interact with a data store like Cassandra or MongoDB. And this falls into the last category, which is we really want people to use concepts, not build them. When you think about a fundamental algorithm like sorting, when was the last time you implemented sorting? And yet you probably use it all the time. The same thing with HTTP. It's not like people go out there and they implement their own HTTP client. We expect that these kinds of concepts, these kinds of ideas are simply available to us, and that we can take advantage of them to build our applications. But the truth is that while we've built a lot of these systems for single machines, we've done very little to expand that world to the world of distributed systems. And so as we look to the future of Kubernetes, and as I talk through where I hope we're going, these are the themes that I'm going to try and carry through. So when we think about building the future of Kubernetes, one of the most important pieces, one of the most important building blocks of that future is the idea of a cluster service. When we're thinking about a cluster, it's not just an API for deploying your application. It's actually an environment in which that application operates. And so we can actually separate out the person who's deploying and the persona of the person who's deploying the application from the persona of the person who creates that environment. And in fact, if you deploy lots of applications into a single environment, you can actually multiply the skills of the person who's developing the cluster environment across all of the different application teams that happen to deploy there. And the way you do that is through cluster services. So a great example of why this is valuable is that these cluster services can provide standardization of the common things that every single application needs. Examples like monitoring and that sort of thing are things that every application is going to need. You don't want every application team to be developing them. And if you can make them automatically available to you simply because an application was deployed into a Kubernetes cluster, you dramatically simplify both the application developer's experience as well as improving the overall quality and reliability of the solution and consistency of the solution. Those are all really valuable things that can be provided simply by the act of deploying into a well-managed cluster. So think about the example of monitoring that I mentioned earlier. If you leave a decision like that up to the teams, you're going to have a bunch of different perspectives. And in fact, the developer personas might say things like, well, you know what, I'm going to use StatsD, or I think I'll use Prometheus. And if the truth is that in many cases, teams won't even know that they need to come up with monitoring until they are in a live site situation and they don't have the monitoring data they need to either fire an alert or figure out what's wrong. And of course, the operator who's trying to get people to take on these best practices, or the systems architect who's trying to ensure that every team does the right thing, is a horrible situation, right? Because you're constantly advocating, you're constantly checking, constantly nannying and babysitting teams. Let's look at how it can be done instead with cluster services. So, for example, if I deploy Azure monitoring into my Kubernetes cluster, or any other monitoring solution really for that matter, from Prometheus to anything else, when I go and create pods, well, Azure monitoring is actually constantly observing the Kubernetes API server. Those new pods get created, Azure monitoring notices those pods. It automatically starts monitoring those pods. And in fact, it can scrape Prometheus metrics from those pods So you can actually build containers, or even if you're using other people's containers that were built for the Prometheus monitoring framework, which is a very popular way of expressing metrics, Azure Monitoring can take that open source interface, take those metrics into it, and then ship them out to a software as a service solution, so that you don't have to worry about, keeping 60 days worth of monitoring data for regulatory reasons, or ensuring that your monitoring system is always staying up because it's a mission critical part of maintaining your application. Instead, you can develop this service that's a part of the cluster, push all that data into a cloud monitoring solution, and really, with very little effort on the part of the cluster operator, and with even less effort on the part of the application developer, have a well-monitored, well-architected system with really minimal effort other than deploying a bunch of componentry into this Kubernetes cluster. And then, of course, once the data is out in the Kubernetes cluster, you want to turn it around, and you can actually then turn around and use open source solutions like Grafana, again, running in the cluster, to provide all of those application teams with all of the dashboards that they need in order to visualize all of the monitoring data so that they can take actions when the pager alert goes off. So I think this is a great demonstration of both the value of a cluster service in terms of simplifying application development, but also the ways in which Azure is integrated with great open source solutions like Prometheus, like Grafana, to really build the best of breed for cloud native solutions that allows you to monitor your applications using these open source tools, but also lifts from you the responsibility for ensuring that your monitoring system, which is one of your most mission critical systems, is always running, always up to date, and always secure. So it's a great combination of the value of a SaaS service with the value of open source components. But beyond the value of these cluster services, there's also this notion of building compliant clusters, ensuring that everybody occupies the best practices for building, deploying, and managing their applications. Because it's great to supply them with a bunch of services, but if the application developer deploys a service that puts the database out on the public internet so that all of your customer data gets exposed to some person who just happens to be scraping URLs, that's a really bad situation. And all the cluster services that you want aren't going to really help with that. You also need more tools in your toolbox. And in particular, you need the idea of creating a cluster that is not just has good services, but is actually a well-configured landing zone. It's a well-configured environment that ensures that the applications that you deploy are reliable, are compliant, and are secure. A critical piece of this, and a good example of why this is such a problem, is that what we've seen is that as people get into Kubernetes and as people start building reliable services, they're going to start deploying lots of clusters. I mean, we would tell you that you need at least 3 clusters to build a well-architected application. You need a test cluster to test your application in. You need at least 2 regions of clusters in order to have reliability in case something goes down. Probably you need more than that for reasons of latency or data locality. So very, very, very rapidly, even a single team is going to end up with 5, 6, 7, or many more clusters running around out there. And just as I talked about how immutable infrastructure was trying to get rid of this idea of snowflake servers, the problem with having all of these clusters floating around is that now you're actually creating snowflake clusters. Right? So you've created a whole bunch of Snowflake Kubernetes clusters. They're filled with immutable pods, and that's great. But if your monitoring system is different, a different version or a different program, even worse, amongst all these clusters, or if the intrusion detection software is running in one cluster but not running in another cluster, you have a really big problem, and it's very hard to ensure the kind of compliance and security that you need for a modern application, especially in regulated industries like healthcare or financial services. Fortunately, we have a great deal of enterprise experience in Azure, and we've really thought about how to solve this problem. But as we start to think about it, especially in the Kubernetes environment, it's incredibly important that we solve it in an open way and in a way with the community. And so I think this is a great illustration of the way that we think about open innovation and open source within Azure and within the Azure Kubernetes service. In particular, we start with a customer problem. we always want to be centered in a customer problem. In this particular case, it's the problem of a proliferation of Kubernetes clusters. We take that problem and we try and solve it as an open source project. We try and develop an open source project that addresses that user need, can work with Kubernetes anywhere, and hopefully will attract a community of developers. In particular, in this context, you're going to see that we have worked with the Open Policy Agent, which is a CNCF project, to develop a solution called Gatekeeper, which is an open source policy solution that works with Kubernetes clusters anywhere. And then we've taken that solution, we've brought it back into an Azure product. We've brought it back into the Azure Kubernetes service so that not only do you have a solution for implementing policy for Kubernetes, but you can actually have it be a supported, managed part of a complete Kubernetes solution from a cloud provider where you know that it's going to work, and where if it doesn't, you can go and talk to our support. So we've gone from an unhappy customer with a problem through an open source project to an Azure product to hopefully on the other side a happy customer who's using the Azure Kubernetes service and can manage their clusters and ensure that every single cluster is identical. So let's take a look at how policy in Kubernetes works. Well, of course, if you're familiar with Kubernetes, you know about RBAC and you know about access control. And let me tell you that if you're putting out any sort of workload in Kubernetes, you need to be configuring your RBAC correctly. That's going to keep out the really bad actors. It's going to keep out the people who shouldn't be accessing the cluster. But what about the people who do have permissions? Right? Just because you have permissions to access the Kubernetes cluster doesn't mean that you're necessarily going to always do the right thing. You may not do things badly on purpose, but there's a lot of mistakes that you might make. For example, where are you pulling all these images from? Maybe you're pulling images from the internet. That's probably not a great idea. Are you launching a new service? Did you get a security review? Or even something as simple as, what's your team's mailing list? So if I see a problem with one of your containers, or I have a noisy neighbor from one of your containers, I know who to contact to find out, to fix the problem. All of these questions are things that are not solvable in Kubernetes as it's initially deployed. But fortunately, they're all solutions that you can solve with the application of Kubernetes policy. And you can think of Kubernetes policy in the Gatekeeper project as being a way of standing in between the user and the Kubernetes API server. In fact, the agent is deployed as an admission controller, and what it does is it takes a bunch of rules. For example, you might say something like, you can only create pods where the image comes from my container registry. It enforces those rules at the time when the API request comes into the Kubernetes API server. And so that means that if a user comes along and tries to create a pod that references an image that isn't hosted on your image registry, the creation of that pod will fail. Likewise, if they try and create a deployment that doesn't have a mailing list attached as an annotation, if you've expressed that rule, that deployment will fail. So policy and policy enforcement becomes a great way to ensure that every application that you deploy to these clusters follows a set of rules that are dictated either by regulators in your industry or by company policy or both. And you can see here a pointer to the GitHub project that is Gatekeeper. And in fact, you can use this project with Kubernetes anywhere. It's nicely and tightly integrated with the Azure Kubernetes service, but no matter where you're running Kubernetes, Gatekeeper can work for you. But of course, this is all about enforcing policy on a single cluster. And I was talking earlier about consistency across a lot of clusters. And so when we think about how we can enforce policy across a lot of clusters, the first thing to do is to take those policy rules and instead of storing them locally on a cluster or locally on a single machine, store them up in Azure. So you have a single point of reference. And then, of course, we can take a lot of clusters and we can point them all at the same representation of policy in Azure, push it to all of those clusters, and now you have exactly the same policy enforcement present in every single cluster that you create. That level of consistency ensures that no matter where a user is deploying their application, the same set of rules apply, the applications look the same, they feel the same, they have the same set of annotations and the same security profile. So it's a huge step forward in terms of managing all of those different Kubernetes clusters at scale. And you can easily imagine that if each individual team needs 5 clusters across a large organization, and we see this all the time, there's dramatic sort of Kubernetes cluster sprawl that occurs throughout both the cloud and on-premise environments. All right, so I talked a lot about compliance and cluster services, about how we create environments that enable people to successfully deploy their applications. But another vital component of Kubernetes is actually the development of those applications themselves. And while Kubernetes has made great strides to make the deploying and managing of clusters and of applications in those clusters much, much easier, it's honestly done very little to help people with the development of the applications themselves. So when we think about developing distributed systems, the basics of a distributed system are something that, if you're lucky, you looked at in your final year of undergraduate computer science education. Many people learn it on the job, learn it from a book maybe. If they're lucky, or if they've had a bunch of experience, they've maybe learned the basic concepts of distributed systems. But then, once having learned those concepts, we ask people to implement those ideas over and over and over again. Right? There is very little ability to share or to reuse the concepts of distributed systems beyond a book. Right? And that's really problematic because it means it's very hard for people to do the right thing. It's very hard for us to share and collaborate. And I think that when we look at Kubernetes, it's not really helping. Kubernetes is the assembly language that distributed systems are compiled to. It doesn't have within it, currently anyway, the tools to make developing those applications particularly easier. And this is, I think, the most important area for us to think about in terms of developing the future of application development on Kubernetes. And certainly I expect it's going to take, if it took us 5 to 6 years to get us this far with the infrastructure side of Kubernetes, it's going to take us another 5 years to get to the same level for developer productivity. Let's take a look at why this is such a challenge for people. When people think about building services, they often begin with an idea of what development environment am I going to use? They think, well, maybe I should use functions as a service. Or maybe I should use a 12-factor web app pattern or platform as a service. Maybe I should just use bare containers. It feels like a very big choice. And it's a big choice that people make possibly before they've even written a single line of code. That's a real problem, right? Because it turns out that if I make the wrong choice here, I could get stuck, or I could even have to rewrite my entire application because suddenly I can no longer scale, or my application is so complicated that a large number of little functions running all over the place is difficult for me to keep track of, and I keep breaking it when I roll out new functions. Or I could start with containers and take 12 months to build an application that I could have built in a month if I had chosen a higher level platform as a service program. So this choice is both hard for people, and it's also way too sticky. Let's take a look at why that is, though. Why is it such a big choice for people to decide if they want to use, what sort of application development framework they use? Well, fundamentally, one of the biggest problems is that historically these systems have been built as silos. Right? They've been built as complete verticals all the way down to the machine itself to provide functions as a service, or to provide web apps as a service, or a no-code solution, or Jamstack, or whatever you want to do. Each of these is developed as a vertical silo with very little crosstalk. So that means that if I decide to build my application in a 12-factor web app, but there's a piece of that application that is way better suited to be a function, it's very difficult for me to get those two pieces to interop with each other. It's very difficult for me to have a single deployment for those pieces. It's difficult for me to package the code up. It's just these silos have been built to favor the experience of the silo over the idea that a real application is actually going to span across all of these silos. So even something as simple as service discovery becomes quite difficult if you're talking about trying to connect from a no-code solution down to a raw container running in Kubernetes. So one of the very first problems is this idea of the silo. But the other problem is that a lot of these platforms come with cliffs, right? Where it's fantastic for as long as you're in the confines of the area. As long as your function fits within the confines of the functions as a service environment, it's beautiful. But the minute that function needs to run longer, say, than the functions environment says is possible to run for, or needs to consume more memory than the functions environment makes available to you, you hit a cliff. And if your entire experience so far has been built on your whole operational model, maybe even your operational hiring, has been built on this idea of an auto-scaling, always available functions as a service, when you hit that cliff, it's really, really, really steep on the way down. You largely have to rebuild your entire application from the ground up to get around the fact that you've hit this limitation in the platform as a service. And historically, this has been sort of the Achilles heel of platform as a service, that there's always a cliff somewhere. Maybe it's accessing native code. Maybe it's memory limits in a functions as a service environment. Maybe it's the set of plugins that are available in a no-code environment. There's always a cliff somewhere in these platforms, and the trouble is that the drop-off largely involves you re-implementing everything that you have. So these two things together, both the idea of a silo and the idea of these cliffs, have made the choice of a programming environment very, very fraught and very, very hard for people as they sit down to build distributed systems. It really shouldn't be this way, and let's take a look at how we can ensure that it's not. Well, the first step is to recognize that actually under the hood, every single one of these programming environments can actually be expressed as a compiler to a container. You can take a functions as a service experience, wrap it all up all that code, and place it in a container. Similarly, for a 12-factor web app, you can, Heroku or Azure App Services or whatever your favorite web app environment is, take that, package it up as a container. No-code solutions are similar. You want to do a no-code workflow or some other logic apps, you can imagine taking that no-code experience, wrapping it up as a container. Similarly for Jamstack and anything else, right? Why is this important? Well, it's important because it helps remove that cliff. If I hit a memory limit in functions as a service and I can eject, if you will, from that environment into a raw container, well, I can take that container and I can run it on Kubernetes and I can just give it more memory. Sure, the operational aspects of it have gotten harder, but the programming environment has stayed exactly the same. And so I have sort of a little bit more graceful degradation. I don't have to relearn everything all at once or rebuild everything all at once. Instead, I can, solve the problem that I have. I need more memory, while retaining the things that I like, the development environment. And over time, if gradually all of my applications become more and more like they're built out of raw containers, that's fine, because I'm learning along the way. Also, because Kubernetes provides base implementations of things like service discovery, replication, automatic restart, and that sort of thing, the silos have also been broken down. So instead of these big, very disjoint silos that don't ever really speak to each other, if we think about taking all of these platforms, making sure that they compile to containers, and that they all use the underlying concepts and the underlying assembly language of Kubernetes, then we really are taking a lot of steps to ensure that the walls between the silos are much lower than they were before, and that building an application that interops between all of these application development environments becomes very feasible. I can express my entire application as a Helm chart, or as a collection of Kubernetes YAML files, and deploy the function, the web app, the no-code solution, the bare containers, Jamstack, all in a single deployment, represented as a single Helm chart, for example. That's a huge step forward that means that the choice of platform is not nearly so monolithic and not nearly so high stakes as it was in application development patterns of the past. But so far, this has really talked a lot about how the development environment that exists around the code, but it hasn't really talked very much about the code itself. How do we actually make it easier to write the code itself? Because obviously, the application development environment is only as good as the code. And when we talk about silos, one of the main problems of the silo isn't just the runtime of the silo, but also that the programming language experience and the capabilities of that programming language experience are different. Sometimes they're even tightly bound to particular programming languages. And so if you want to program in a different language, or you need to integrate a library that's written in a different language, you're out of luck. So we're actually doing a bunch of work to solve this as well. And in particular, I think the pattern that has emerged in Kubernetes is this idea of a sidecar pattern. The reason a sidecar is so powerful is because it becomes kind of like a running shared library, right? Where a shared library was something that you linked into your application, it lived on the machine alongside the application. A sidecar is actually a running container It's an application that is running independently, distributed usually by a third party, but running alongside your container and providing capabilities and abilities that that your main application container can take advantage of. Sidecars have been popularized by things like service mesh, by monitoring solutions, and many others throughout the Kubernetes ecosystem to provide extended capabilities delivered as running processes by third parties. And it's a hugely powerful pattern. So we're going to take a look at a particular one that we have built called Dapr, which is the Distributed Application Runtime. It's an open source project. It's available. You can check it out at dapr.io or up on GitHub. The whole idea behind Dapr is to take these componentry of how you build a distributed system and make it available to you as a sidecar through a simplified interface. So let's think about something like storage. You know, ultimately, if what I want to do is do key value store, the interface to storing a key and a value to a key is pretty simple. I just want this key to have that value. It's not very hard to understand. But of course, when I actually want to interact with a real data system, I have to worry about things like authentication. I have to worry about things like sharding. I have to worry about things like reliability. I have to worry about all of these intricate aspects of the specifics of the data store. But most of the time, that's actually not, necessary. And so what Dapr actually allows you to do is to have a simplified HTTP interface to a simple storage interface. And that storage interface can be bound to any particular implementation, whether it's Cassandra or Redis or a cloud-based service like Cosmos DB in Azure. You can have exactly the same programming interface for that storage. And you can actually have the same code even use different storage implementations in different environments. Maybe in Azure it makes the most sense to do that storage in Cosmos DB, since storage is hard to maintain by yourself and it's much easier to use a cloud-based solution. But out at the edge, maybe you want to use Redis. It's a much smaller, lighter weight solution, much more suited to running on hardware like a Raspberry Pi or a small-scale Kubernetes cluster out at the edge. And maybe in a different cloud or in a private cloud environment, you have someone running a large-scale Cassandra cluster for you, and you're willing to use that service in that environment. Well, without Dapr, people would have to write those interfaces 3 different times, have a big switch statement or configuration file or some other way of switching between them. With the Dapr sidecar, you can easily interface with the exact same interface, target all of those storage solutions. The sidecar worries about things like authentication. You just need to talk HTTP over localhost. And because it's a localhost connection, you don't have to worry about authentication. It really simplifies the programmer's task of developing. And it's important to realize also that because it's a container sidecar, and because we think about functions as a service running in a container, or web app running in a container, that sidecar can run alongside wherever your code happens to be running and provide the same set of capabilities. But it's not just about storage, it's not just about interfacing to storage systems, it's also about things like events. You may just want to have a piece of code that runs when an event occurs. And it doesn't really matter whether that event comes from Kafka, whether it comes from Azure Storage, whether it's an event in Kubernetes. You just want a little piece of code to run. But interfacing with these eventing systems is likewise challenging. It requires you to learn lots of details, different protocols, all sorts of complexities that really have nothing to do with the concept of, hey, look, I want to just respond to an event. And again, the Dapr sidecar can provide these capabilities as well. So Dapr can come and say, hey, okay, we know how to listen. And as a community, we've developed a best practices version of listening to a Kafka queue, dealing with sharding, dealing with multiple listeners, dealing with all of the intricacies. You as a developer, just use the sidecar, say you want to listen to this Kafka queue in your Dapr config, make a simple HTTP call, or in this case, receive a simple HTTP call, and that's it. The event is delivered, and you can move on and focus on writing your application code. Right? So the Dapr runtime enables us not just to have things be easier, but also to have a community around developing these best practices. And of course, the other value of the sidecar is that because the interface is across the network on localhost in HTTP or gRPC, you can choose whatever language you want. You can write your code in Go, in .NET Core, in Java, in JavaScript, TypeScript, Python, Rust, C++, whatever language you want, as long as you can make an HTTP connection, you can use the code that is written in Dapr. Right? So again, we're not, Dapr isn't locking you into any particular environment. It's really focused on providing a core set of capabilities, a common implementation that the entire world can come together and build as a best practice, and that developers can rely on to simplify their application no matter where it's built or honestly where it runs. I want to talk very briefly about serverless because that always comes up as part of the functions as a service. I think that serverless is sort of overlaid because serverless oftentimes has meant a programming model where they really mean functions as a service. And we've talked a lot about those functions as a service. But when I think of serverless, what I really mean is, hey, look, those servers are going to disappear. And we're not going to worry about servers anymore. And in fact, in Azure, we're building serverless container infrastructure such that instead of having a bunch of machines, you actually just have a bunch of containers running in the cloud. Right? But of course the question is, if you can run just arbitrary containers, arbitrary processes out in the cloud with all of their sidecars and everything else like that, what about orchestration? I still need to do all that stuff that I talked about in terms of orchestration. I still need to replicate, define services, and all that kind of thing. We don't want to reinvent the wheel. We've got a great open source orchestration API out there. So we're going to take this serverless container infrastructure that we have in Azure and in other clouds, and we're going to interface it into Kubernetes. So in addition to having a Kubernetes API that spans across machines, we have a Kubernetes API that can talk to serverless container infrastructure also. We've created this virtual kubelet project, which is an open source project out on GitHub. You can see the address there, to do precisely this, to define the concept of a virtual node that is connected to serverless container infrastructure so that when you schedule an application in Kubernetes, it can go and run without actually ever being on a server. And over time, I think these virtual nodes are going to replace all of the virtual machines to the point where we really have a serverless Kubernetes. And there are no more machines for you to worry about. And we really do live that promise of providing you with a container abstraction with literally nothing else to see. It's actually been interesting to see, as we've thought about the idea of virtual nodes, the other partnerships that have come in through this channel. And in particular, we've seen people use virtual nodes for interfacing with IoT devices, virtual nodes for bringing WebAssembly into Kubernetes, and a number of different interesting partnerships around this idea of having something more than a virtual machine be a participant and a place where you can run things inside of a Kubernetes cluster. And so I think that's a final great example of why open source is so valuable to us and why open source is such a great place. Because we built something for one purpose, for one customer need, and by building a community, we've unlocked a large number of people to come together and collaborate to focus on their specific problems. In conclusion, Kubernetes has, in its past, across the last 5 or 6 years, transformed the way that we operate our applications. As we look to the future, it's going to be defined by the ways in which we enable the developers to do a better job building those applications on top of Kubernetes. Thank you.